I tried it myself and I never succeeded. So that's why I need like people like my friend with the kung fu skill to do it, to cut the tip, to make sure it's atom size, right? If it's not atom size, your experiment is not gonna work. So I started recorded already. Good afternoon, everyone. You bought both of them, haven't played yet. Are you talking about the potato battery or STM? The STM tabletop can buy, but you need like special. It's like I think 10,000 Singapore dollars. So like 40 50 RMK Malaysian ringgit, something like that. So yeah, the reason why I started to show these videos about quantum tunneling is because we will reach that soon. I don't know whether we have enough time to cover this towards the end, but eventually we will talk about quantum tunneling, but I will not do all the calculations. So I'll just show you the main concept, and then the details of the calculation is nothing special, it's just very long and tedious. So all of the details are in the lecture notes. So we'll leave it there, but for now, let us study the simple case first, right? Let us study the delta function potential. So we are at the third example here. Just now, in previous classes, we got the infinite square well, and then last class we did the free particle. So right now we're doing the delta function potential, which is to say that this is a configuration where the potential energy is just the delta function, and then it has some constant. So it's some number. So let's say it is some positive constant, right? And there's a negative, so which is to say that my graph of my potential energy looks like this. So this is my x-axis here, and let's say this is x equals to 0, right? Then my potential, remember the definition of the delta function, is 0 everywhere whenever inside this argument is non-zero. So is 0 everywhere except when my delta function is 0, is going to be infinity. And then this is negative, so it becomes a negative infinity. So it's suddenly it's a very sharp spike downwards, right? And then immediately after 0, it come back to 0 again. Immediately after x equals to 0, it come back to 0 height again. Okay, so this is my delta function potential. Okay, so this is negative alpha delta x. So we want to solve this problem now. And as before, I like to call this region 1, and this side is called region 2. Okay, so this one is just x equals to 0. It's just 1 point. So how do we solve this problem? Well, we do our usual thing. We do the Schrodinger equation. But previously, I remember I was just before the end of previous class. I was talking about the difference between the bound states and the scattering states, right? So bound states are where energy is less than the potential energy when you go to infinity. So it's going to be energy anywhere down here, right? So any values of any negative energy is going to be a bound state, and positive energy is going to be a scattering state, right? So bound states. So let us solve case by case. Let's consider a bound state solution first. So bound states. So the bound state solution. Yeah. So box. Okay. So bound state solution is where my energy is negative, so that my delta function potential, right, is like this. Then my energy is here. Okay. So see, as I go far away, my energy is less than my potential. So how do I solve this Schrodinger equation? Well, I have two regions. We go with region 1 and 2, one by one. Starting with region 1. So in region 1, on the left side, my potential energy is just 0, right? So it's actually very easy. My potential energy is 0, so it's h squared over 2m. Second derivative, this is my time independent Schrodinger equation, is equals to e psi. So my second derivative of psi is equal to negative 2me over h bar squared. Remember that the energy itself is a negative value. So let's put this in. So this is a coefficient that is positive or negative. So this thing here is a positive coefficient. If this is a positive coefficient, what is my general solution? You learn this in ODE, right? Depends on whether this is positive or negative. It is an exponential, right? So if this thing is positive, then this is an exponential. So it's negative a kappa x plus another constant e positive kappa x, such that my kappa constant is the square root of this. So it's square root negative 2me square root over h bar. Okay, so I got two terms, but I can already tell you one of them should be 0 because I'm talking about a region 1 solution. Region 1 solution is where I'm talking about negative x, right? Negative x. So negative x, then if x go to the left side, as I go to the left side, this term is going to be infinite. So we don't want this to happen. If I go all the way here, this term is going to be infinity. If this happens, I cannot normalize my wave function. So let's say that this one will explode if x goes to negative infinity. Therefore, we set a equals to 0, so that my solution in region 1 is only this constant e to the kappa x, and this solution is valid for x less than 0, and the kappa is given by this. Okay, so we got kappa, we got the solution in region 1 already. Then going on to region 2. Is everything running smoothly? Let me see. Testing. Yep. Yep. Oh, Portal 1 and 2. Okay. Oh, you haven't played. I guess you can play Portal 1. You can probably finish Portal 1 in like 3 hours, 2 hours. Portal 1 is very short. Portal 2 is much longer. But Portal 2 is where the potato battery comes in. Okay. So let's go to region 2. Region 2, V is still 0. Right? So V is still 0. Then we get the same Schrodinger equation and therefore the similar looking solution. Just that we got the constants may or may not be the same, right? So same story happening here, but this time my x is positive now. Okay, so my general solution is well, psi of x is equals to for this differential equation is two terms, right? Two possible solutions. Then there's going to be two different constants. So to avoid confusion, we should keep them separate. So let's call them C and D, right? And kappa is the same, which is to say it's 2me over h bar square root. And then, but now, which term should be 0? So now I'm talking about positive x. So positive x, right? Kappa is a positive number. If this thing goes to infinity, then this term will explode. So this term will be infinity if x goes to positive infinity. Therefore, we set d equals to 0, and such that we have a solution for region 2, which is c exponential minus kappa x, right? So this is pretty nice because we have two exponential solutions. This one exponential dropping off to the left, this one exponential dropping off to the right. Okay, so now let us try to let's write down the solution. Let's compile the full solution. So solution is my wave function should be having two regions. On the left side is b kappa x for x here, and then c e negative kappa x, where x is on the right, and my kappa itself is negative 2me square root over h bar, right? Remember, we are talking about negative values of energy here, bound state solutions. So how do I determine B and C? Well, we use the continuity because the wave function must be continuous, right? Our assumption here. So in x equals to 0, we have two regions separating region 1 and region 2. Okay, and then we require that my wave function when on this side going to 0, it should match with this side going to 0. Okay, which is to say that b e to the power 0 is equal to c e to the power 0, so b equals to c, right? Therefore, we update our solution. My wave function is both are b e kappa x, c e negative kappa x. This is for x to the left, this is for x to the right. And then if you plot the graph of my wave function, is going to look like this. So this is psi of x. This is not the probability, but this is, oh, both are b, right? So both are equal to b. So both are exponential functions on both sides. Okay, so we got this b here, and then we can still determine b because we normalize the square of this graph. The area, after you square this, you get a new graph. The area should be 1. The sum of probabilities to be 1. That is our normalization, right? So for our normalization, I want the integral of psi absolute value square from infinity to infinity to be equals to 1. So when x is negative, my function is this one. So that means it's from negative infinity to 0. It is this thing absolute square. So be careful, avoid making mistake. Right, I think it's very easy to forget to square this. Okay, and then we got e to the negative, positive, and then square, right? But everybody here are real numbers, so 2 kappa x integrate with respect to dx, and then on this side is absolute b square, e to the negative 2 kappa x integrate this with respect to dx, right? So this is my normalization. So both sides, both terms have a factor of b square. And then I just need to integrate this one. So this one, it will give me 1 over 2 kappa, right? And then e2 kappa x from negative infinity to 0. And then plus negative 1 over 2 kappa come down. And in negative 2 kappa x, the limit is from 0 to infinity, right? So 2 kappa, I take it out. So this is just absolute b squared over 2 kappa, and then if I put in the limit, e to the power 0 is 1, negative infinity is going to be 0, and then over here is minus 0 plus 1. So this is actually just 2. So this will cancel with the 2 here, and therefore we find that b squared is just equals to b squared. Well, we want the equation to be, hang on. We want the equation to be 1 equals to b squared over kappa, right? Which is to say that b itself is equals to square root kappa. Okay, so yeah, square root kappa. I think I just realized that the lecture notes might have a mistake, right? So I remember lecture notes is 1 over kappa, but let me correct this. Okay, so let me try to so let's do everything correctly. This is kappa. In other words, let's update the solution, right? So this is so absolute value, this thing, and just to like make everything official, we should choose, because technically b can be any complex number where the absolute value is this thing, but let us choose b to be a real number, so it got this, right? So that means we can update our solution. Which is psi of x is equals to b is kappa e to the kappa x whenever x is negative, and square root kappa e negative kappa x where x is positive. So for the purposes of something that we'll need later, I will need the derivative of this function. So if I differentiate this, I just get kappa kappa e kappa x, and then if I differentiate, I just get kappa kappa e negative kappa x, right, for x negative, and then over here for x positive. Okay, so we are going to make use of this in the next page. By the way, before I continue too much, does anyone have any question? Yeah, good. Play after midterm. So after you finish all the exam, you can enjoy, relax with Portal. Okay, so we got we got these two, we got solution and the derivative now. Notice that for this solution, right, this one is a bit weird. We seem to have determined the wave function without using any information about the delta potential, right? Because our delta function potential, it depends on the alpha here. So alpha is like kind of like the strength of the potential energy, right? So if alpha is very high, we can imagine this is a very negative potential energy. Even though this is infinite, but there's some alpha here. It's a bit weird, I know, right? We have found the solution region 1, region 2, right? And there's no information on alpha coming in. But what we can do is we can integrate the Schrodinger equation, and that will implement the condition for the energy, right? So we have determined the wave function. Yes, we have determined kappa in terms of E, but what is the possible values of E, right? So we don't know yet. That is what we want to determine. So energy here is a bound state. Since it's a bound state, we expect the energy to be quantized, but what is the value? So let's determine that. Okay, so to find E, to find the value of E, we integrate the Schrodinger equation. Okay, and we just integrate the Schrodinger equation from a region that contains the delta function. So we go from negative E to negative epsilon to positive epsilon, right? What is happening here is, well, my graph is like this. My delta function is from here, and then at x equals to 0, there's a spike, right? So we are just integrating from negative epsilon to positive epsilons, right? So this is 0. So we want to integrate this function. It's 0 everywhere except for this spike. So something interesting is going to happen here. Let's find out. Okay. So the Schrodinger equation itself is h bar squared over 2m d psi dx, and then plus the potential, right? So plus v psi equals to e psi. Okay, so that's my Schrodinger equation. The spike at x equals to 0. So should I remind? Let me remind you that the delta function, right? The delta function. So I should do this in the front. Is there space in the front? So the delta function definition says that delta x minus x prime is equals to infinity when x is equals to x prime, and is 0 for x not equals to x prime. Okay, so in this case, this is the case where x prime equals to 0. Do you get it? Right, so this is x prime equals to 0. Right, so when x is equals to x prime, you get the spike. Right, x prime is some constant, x is the variable here. Okay, so yeah, remember the meaning of the delta function. Yeah, I should have mentioned this at the beginning. It's been quite a while since you used delta function, was it? Well, a few 1 or 2 weeks. Right, get it right? Why is there notification? The boundary potential must equal delta function. No, not the boundary. It's in the middle of the system. Right? It's in the middle. Yeah. So it's a potential energy where it's 0 everywhere. The potential energy is 0, and then suddenly it's very, very negative in the middle. Okay, so this is my potential energy. Make sense? Okay. So while you think about this, let me write down the next line of this equation. Basically, we just want to integrate this equation. So integrate term by term. Right. So integrate from minus epsilon to positive epsilon, second derivative dx, and then I am integrating a v psi, right? So remember, my delta function is equals to negative alpha delta x. So this is the integral of negative alpha delta x times my wave function, and I'm integrating this with respect to dx. So I'm integrating from minus e to positive e, and then this one is disturbing. But on the right hand side is e is a constant, no need to integrate. So I'm just integrating my wave function from minus epsilon to positive epsilon. So this one is, well, this one is integrating a second derivative. So therefore we can kind of, this is kind of saying the fundamental theorem of calculus. It is, after integrating, this is just basically just the derivative epsilon minus derivative at negative epsilon, right? Fundamental theorem of calculus kind of argument. And then, right, this thing, well, let me write one more line. The alpha is a constant. This is epsilon to epsilon delta x psi x. Integrate this with respect to dx. This one over here is epsilon epsilon psi x dx. Okay. Okay. So I think I will go a bit slowly because you guys are not used to delta function yet. So let me see if you have any questions. Yes, correct. Yeah, that's why we want to do epsilon epsilon. Yes, because there's a spike. If there's no spike in my, if I just integrate from positive 1 to positive 2, there's no spike, then the whole thing becomes 0. Yeah. So we purposely want to see what happens at the spike. Okay. Okay, any other question? So let me write one more line here. H bar square over 2m, right? So this is the upper limit is my delta function at positive epsilon minus the derivative at negative epsilon, so positive and negative epsilon, and then the delta function, wait, I already written like this, delta x psi x. Okay, sorry, this line is redundant, but let me show you what happens at the delta function. So remember the meaning of the delta function. It contains the spike, right? It contains the spike. So therefore, this integral is not 0, but the purpose of the delta function is I'll just pick out the value of the function at the spike, and the spike is at 0. So this is going to be the value of my wave function at 0. And what was my wave function at 0? My wave function at 0 is, you plug in 0, right? Or you take the limit to 0, is basically just square root kappa. Right? So over here is square root kappa. And then now what is this? So this is the derivative at positive epsilon. So it's on the right hand side. It's on the right side. So on the right side, my derivative is kappa root kappa, right? So this one is kappa root kappa e to the power of negative kappa epsilon, right? So you just put in positive epsilon here. Okay, and then for this one, well, what happens here is this is on the left side, so I should use the region 1 solution. So the region 1 solution is negative epsilon, so I plug in negative epsilon is kappa root kappa e to the power of negative kappa epsilon. Okay, so yeah, we are doing everything carefully. So now what happens now is h bar square over 2m. Kappa root kappa can be factorized out. Oops, hang on. It's not just kappa root kappa, it's negative. Yeah, otherwise they become 0, right? So negative negative. Negative negative, so it's minus kappa root kappa e minus kappa epsilon, and then minus kappa root kappa e to the kappa epsilon. So these are two of the same copy of terms, and then I got alpha square root kappa. Okay. So on the right hand side is E integral from epsilon to epsilon psi x, integrate this with respect to dx. So let me know if I made any mistake, because the negative sign is very tricky. Okay, so basically what we have here is minus minus minus, you will get a plus, and then this it will become h bar square over 2m, it will become plus and 2 kappa kappa e to the kappa epsilon minus alpha kappa, and then this is e minus epsilon epsilon psi x integrate with respect to dx, so the 2 will cancel, right? And then now actually all I need is, so this term here I don't really know how to well, we can evaluate, but this term will simplify if I take the limit of epsilon going to 0, right? So if the epsilon going to 0, so what am I left with in this equation? I got h bar square kappa root kappa divided by m, the e to the power 0 is just 1, and then alpha root kappa, and this is equals to well, the integral when epsilon going to 0 is just the integral from 0 to 0, right? So the area under 1 point is 0 area, so this term is equals to 0, and when this term is equal to 0, I can cancel out some factors, right? And I find that kappa is equals to alpha m over h bar square. Okay, alpha m over h bar square. Okay, so I think everything is correct now, and I have found a value of kappa. And what was kappa from the beginning? Kappa was, remember kappa is this one, right? So kappa was equals to square root of 2me over h bar. So if I square both sides, well, let's simplify a bit of things first. I got this thing, right? So I end up with 2me square root is equals to alpha m. Then if I square both sides, if I open the square root, I just get negative 2me alpha square m square. So one m will cancel with this m, and finally I have the result that there is a h, oh, I forgot the h bar. So if I square both sides, it got h bar square. So finally I got m alpha square over 2h bar square. Okay, so I have found the allowed value of energy. Okay, so finally, right, after almost yeah, looks like everything is correct. I almost confused myself because almost forgotten the minus sign, right? But everything is correct now. We got the value of energy over here. The interesting thing about this is that the energy is quantized. It has only exactly one value. So m is fixed, is the mass of the particle. Alpha depends on what is the potential, right? It is the system. It is a fixed number. H bar is also another constant. So there's no variable, right? There's no integer or there's no dependence on any other thing. That means there is only one value. For any delta function with alpha, then this alpha will determine the energy of the bound state. Right, so we have only one allowed energy level. So it's a very, very different from the infinite square where we got integer energy levels, right? N1, N2, N3, N4. Here is just one. That's it. No more. Okay. So there's only one allowed energy level, and for what we have assumed was that we are talking about the bound states. So bound state is for energy lower than 0. So this is my negative energy levels. Okay. So so since we got the full solution, let us write everything nicely, right? Compile the answer. The full bound state solution is what? Is psi of x is equals to, we have got the solution, right? It was square root kappa e to the kappa x. Okay, this is when x is negative, and then square root kappa e to the negative kappa x. This is x positive, and my kappa was given by this formula h bar, and my energy level is given by this formula. So we have all the information of my solution. So this is my answer for the square delta function potential. Okay, page 1, 2, 3. This is page 4. Okay, clear? Any question? What time are we at now? Okay, 4:30. Yeah, it looks like we will have plenty of time to talk about tunneling. Yeah, I guess so, right? So who did it? I have no idea, but it's kind of like almost like a standard practice, because I know it sounds like, oh, very ingenious, right? I think the reason why we do integration is because it's a delta function, right? And probably the inspiration to do this is the idea that the delta function has the definition of x minus some value, right, of some function fx dx is equals to f of x0. So I think because delta function has this special property, then we want to exploit this property. So therefore we perform the integration. So I guess that is the line of thinking, whoever did this. So that is one way to manipulate, right? So but that's the benefit of learning all this now, right? So all these smart people did all these things years ago. Then we just like learning the final result. We don't have to go through the effort of like trying to get the idea of how to do it in the first place. So that's research, figuring out answer that people haven't figured out before. But once you've done it, it looks like very straightforward and is written down in textbooks since then. Okay. Yeah, well, everyone here is on the way to become these people, right? We are learning this technique, So we are learning, quantum mechanics. We are learning this trick. We are learning that trick. We are learning how to manipulate bra-kets. So we are building up all the skill. Okay. So I guess one advice, because there's always the misconception in physics, is that physics is for smart people, and people think you need to be born smart to be doing physics stuff, but that's not true, right? There's only like rare people like Einstein or Edward Witten or things like that. They are born smart, but everyone else is the same as everyone else, same as you guys now, right? Attend the university, study the lecture notes, and things like that. Most people are not born smart, but all of them have to study lecture notes, read, blah blah blah. Yeah, I guess you know what I'm talking about, right? So yeah, if you want to become one of those people, you are on the way right now, right? Yeah, you guys are year 2 already, so almost there. So the next problem that we want to solve is we have found the bound state solution. So what's the scattering state? So scattering state is my potential energy is the spike, right? This is my V. So scattering state is my energy is higher, right? So energy is higher. So this is my scattering state solution. So E is greater than 0, right? And then very far away, my energy is greater than V. That is the definition of the scattering states. So how do we solve this problem? Starting with region by region again. So in region 1 again, h bar squared over 2m, and then second derivative, and then on region 1 my V is 0, right? So this whole thing is 0. So same story here, but now my energy is a positive number, right? So we are assuming E is positive, so that my second order differential equation is negative 2me over h bar square times psi. So this coefficient now is a positive coefficient with a minus sign outside, So this solution is going to be, my general solution is going to be ikx, right? So it's a constant e to the I. I'll just call this k, and then this is b negative ikx, right? And this is for x on the left, and my k is supposed to be the square root of this, so it's 2me. It's a real number, right? E is positive, so the square root of positive number is good, it's real, and yeah, divided by h bar. Okay, so over here, this is a free particle solution, so we can't expect to normalize this, right? So this so this is a scattering state solution. So usually not normalizable. So let's not worry about if x is going to infinity. Well, exponential consists of sine and cosine. So sine and cosine is just going between plus and minus 1. So it doesn't explode, it doesn't diverge. Same story here, it doesn't diverge. And in any case, it's usually not normalizable. But what we can do is, well, we can just continue to solve region 2 and see what happens. Although they are not normalizable, but we will figure out a relation between these constants. Okay, so in region 2, the Schrodinger equation is still the same. Right, so it's the same, but my x is now here, so the general solution is going to be the same, but just to avoid confusing each other, we call them different constants, and the k is the same, right? Everyone's the same. Okay, so k is still 2me over h bar, and this is for x positive. So let us collect my wave function. So my wave function is, the full function is the psi of x. On the left side is aeikx plus be minus ikx, and then the other side is ceikx plus de negative ikx. This is for x negative, this is for x positive. Okay, and later again we will do the same trick, the smart people trick. We will integrate the Schrodinger equation. So I will need the first derivative at least, right? So the first derivative is differentiate this, the ik come out. Differentiate this, the negative ik coming out. So I have a ik, I will factorize e ikx, b e ikx, right? And then same story here, ik c e ikx minus de ikx. Yeah, then this is for x negative, this is for x positive. Okay, so yeah, now let's integrate this Schrodinger equation. So integrate the Schrodinger equation. I guess let me copy the Schrodinger equation for reference. So second derivative plus the potential, right? My potential is alpha delta function, so it's negative constant times the delta function psi of x, and then on the right hand side is e times psi of x. Okay, now I'm going to integrate both sides. So h bar squared over 2m, integral from epsilon to epsilon d2 psi dx squared, integrate with respect to dx, and then minus alpha, integrate epsilon to epsilon, this thing dx, and then on the right hand side is e, integral from epsilon to epsilon psi of x dx. So the same story is going to happen later. We will calculate this, and then we will simplify by taking epsilon to 0. Okay, so yeah, let me just slow down and check for questions. yeah, you guys. So um, um, yeah, let me encourage a bit more, right? A lot of you, you know, your GPA was higher than my GPA when I was in year two, in your year, the corresponding year. So yeah, whether I guess another lesson is, you know, your scores in undergrad may or may not have correlation to what you do later, right? And then yeah, I think I'm told this story. I think I say things like this before, or in a different class. My classmates with high GPA now, like did poorly in the FYP, but then you can also have classmates with very low GPA in year one and did first class honors. So there's all the possible cases, right? So there's almost no correlation between these kind of things. But the main point is, yeah, you need to learn the skill in order to do well. Okay, so I guess now we have digested this a little bit. We can try to work out the next step. It is very similar to what we did just now. The first term is this thing, integrate this, it will become the first derivative. So something like fundamental theorem of calculus is the function at epsilon minus the function at negative epsilon. Am I right? Okay. Yeah. So we got this thing, and then this part is minus alpha. So once you integrate this out, it will just becomes the value of the function at 0. And then this part no need to do anything. It's going to be 0 later. Okay. So now we plug this in, what we have. So on this side is h bar squared over 2m. And then psi prime. So where I did a psi prime just now. So the psi prime at epsilon. So this one, try not to confuse. Positive epsilon is region 2 on the positive side. So it's ik ce ik epsilon minus de minus ik epsilon, right? And then minus the value at negative epsilon. So I use this part. I got ik ae negative epsilon, so it's minus ik epsilon minus be positive ik epsilon. The good thing is, even if you made a mistake up here, doesn't matter because it's gonna be 0 anyway. So that's good. And then the alpha. So no, I just can't decide whether to write here or write here. Let's write here. Minus the wave function at 0. So I'm going to assume is continuity, so therefore I'll just choose one of them. So let me just choose a plus b, right? So which is to say that this is alpha, and then a e to the power 0 plus b e to the power 0, and then on the right hand side is equals to e integral epsilon to epsilon psi integrate with respect to dx. This one is going to be 0 later, so no need to worry about it. Okay, so next thing is I'm going to take the limit epsilon going to 0, right? So that's why even if you make a mistake, you put the wrong negative sign up there, it's fine, luckily, because it just becomes ik c minus d minus ik a minus b, and then this part is just alpha a plus b, and then this part is 0. Okay, so let me tidy this up a little bit. The ik, I can take it outside, so I got negative ik h bar squared over 2m, and then it's just c minus d minus a plus b minus alpha a plus b equals to 0. Okay, and then I shall rearrange this a little bit more. This alpha, I will take it to this side, so I got alpha a plus b, and then once taking this side and then the factor, I go here, so I got 2m over ik h bar squared, right? And then I bring the negative sign over here as well, So I got C minus D minus A plus B equals to this. And I think this one, a lot of you guys ask me all the time because you're not used to it, right? I'm going to use the identity that 1 over I is equals to negative I. So that my C minus D minus A plus B is equals to, minus will cancel the minus sign, so that I'm arranging it in such a way that it becomes a positive 2I. Right, so 2I is up here, and then the physical constant is m alpha over k h bar squared, and k is given by square root 2 me over h bar. We'll fix this later, but I got A plus B now over here. Okay, so now in order to simplify my notation, I'm going to call this just beta, right? All these are a bunch of constants. You multiply everything, you just become some other number. Let's just call this thing beta, so that C minus D minus A plus B is equals to 2I beta times A plus 2I beta times B. And then there's an A and B over here, so let's try to collect them together. Let's bring the A to this side. I got C minus D is equals to A going there, it will become 1 plus 2I beta A, and then B becomes a negative B, so I'll pull out the negative sign, and then I got minus 2I beta B. So that, yeah, it's correct. So I got this relation between the two constants, right? So by integrating the Schrodinger equation, I found the relation between the quantities that we have. Okay, so we are almost done. I just need one more condition we can make use. So I have actually, how many variables do I have? The beta depends on the situation. What is the mass of the problem? What is the potential energy of the system, and all that. These are integration constants. So these are variables that we want to fix, or fix as much as we can. We have A, B, C, D. We have 4 of them. We have one equation. We can get another equation by making the continuity, right? So continuity at x equals to 0. So when x equals to 0, my wave function should be continuous, right? I got region 1, region 2. Okay, so my wave function at region 1 should be equals to my wave function at region 2. And what was my two wave functions? On the left side, it was, a lot of paper everywhere now. My wave function was, on the left side is A plus B. On the right side is C plus D. Okay, so I got a second equation. Okay, so I got equation 1 and equation 2. Equation 1 and equation 2. So we are almost, this is as far as we can go, right? So that is the two relations that we can use to determine the relations between the two parameters. So that is as far as we can go, our solution already. So our solution is, because remember, this is a free particle solution, so we can't use the normalization condition. Even if we try, we are just going to get infinity. Okay, so, and the reason, if you recall, it is because we are considering a single k. This is just a single eigenstate of the Hamiltonian. Okay, so for a realistic solution, you need to consider a superposition of various k to get a wave packet. But for now, let us compile our solution. So our solution is, my wave function is A e ikx, right, plus B e minus ikx, and then this is for x negative, C e ikx plus D e negative ikx, this is for x positive, and then our k was 2me over h bar square root, and yeah, I think that's it. And the constants are related by the previous two equations that we have just derived. So constants are related by this and that. Okay, so what we have here is 1 plus 2I beta A minus 1 minus 2I beta B equals to C minus D, and then I got A plus B is equals to C plus D, and furthermore my beta was beta is just a shortcut for M alpha over KH bar square, and this K is given by this. So shall we put this now maybe later, right? So we this K is the same as this K, right? So if you plug this in, you're gonna get another mess. So for now, let us keep it this way. Okay. Yeah, any questions? C minus D minus A plus B. Yeah, it kind of sounds nice, right? Yeah, I mean, you guys will definitely think this way now lah, but you know, but there's plenty of time to practice. Yeah, that is also true, right? The reason why you guys are learning like calculus, linear algebra 1, and all those things is because we will use this. We will use all these weapons to handle these problems here. Okay, so that is why. It's a bit early, but the next thing I'm talking about is kind of a different thing. So I guess, yeah, might as well let's just take a 10 minutes break. Okay, and then because eventually we will go to the problem of quantum tunneling. So yeah, might as well let me stop the recording here, and then we'll take a 10 minutes break, and during the break I will show you the video of the tabletop. Okay, so picking up where we left off, the next thing I want to talk about is the scattering states in particular, right? So scattering state is where as the particle goes far away, the energy will be higher than the potential energy. So that means the main point of scattering state is the particle can go to infinitely far away. It is opposite from bound state, like the infinite square well, right? The everywhere far away the potential infinity, so you can never have energy higher. So therefore potential infinite square well is a bound state. It is trapped between the from 0 to A, the length of the box. So now we want to focus on the scattering states, and I will introduce two things related to the tunneling, right? So tunneling is where one particle can jump into another region for some thanks to the magic of quantum mechanics, right? So this is what we call the transmission, and the other case is the reflection. So transmission and reflection of scattering states. Okay, so so for here, let's consider positive K. So we consider solutions where K is positive, and then let me recall that EIKX, right? These are representing particles moving to the right. Okay, so E negative IKX are particles moving to the left. So yes, even though I said we can't define velocity using a wave function, but was it Zuri who suggested, which is true here, we do have the wave velocity. So we can use the wave velocity, but it will not be exactly the same velocity as the Newtonian mechanics velocity. But in any case, there is some direction involved over here. So we can definitely talk about direction, no problem. So so we can talk about positive K, it will particle go to the right. Negative K means particle moving to the left. Okay. So now we can study this problem now that we understand the this meaning, right? So now we consider a scattering state on the delta function potential. Scattering states solution of the delta function potential. I think I'll just draw it. We have written so much of it just now already. So let's just draw it. My delta function potential is, the spike is at 0, x equals to 0. Okay, so this is x equals to 0. This was region 1, this was region 2. Okay, so we got two solutions, right? So on this, the wave function on this side is exponential ikx, and then plus b exponential minus ikx. And then on this side, we got c e ikx plus d e negative ikx. So now, remembering this, now we know what is the meaning of this part of the solution, right? So this solution is the wave going to the right, and then this solution is a wave going to the left. Okay, so this is wave to the right. This solution is wave to the left. Okay, so now we consider a situation where the particle is incident from the left. Okay, so what this means is, let us say, right, if a particle that is coming on this side, okay, what is my solution? So using this description, we have a few possibilities of solution over here. Is that when a particle is coming in, right, what happens after this? Well, it will be either reflected back, so it will be this term. So this term is a reflection, a reflected wave. Reflection means, it just means bounce back, okay? Or it could continue to pass on. This is transmitted wave. And this is the incident wave. Okay? So if this is incident, so if a particle that is coming in one direction, there is obviously only two outcomes, right? Either you see it coming this way, bounce back, or it continue to move on. So it's either reflected or transmitted. This part is a particle coming in from another direction, so it has nothing to do with my original incident particle. So what I'm trying to say is, this part is not relevant. Agree? Right? So I'm just trying to list down what is the possibility that for a particle is coming in this direction, what are the possible solutions of my wave function. This is my full solution. But if I'm just focusing on the case where my particle is coming in from the left, then it's only either reflected or transmitted. This solution will be describing some other particle coming from elsewhere, so I don't want to talk about this. Okay, so that means the part is not the term ikx is irrelevant to our discussion. So we set d equals to 0, right? So we set d equals to 0. So therefore, my wave function now is just aeikx plus beikx negative. This is for the left side, region 1. And then this part has only cikx. And then this part positive. Okay, and then my equation, my previous equations that we had just now, my constants are related by this, right? So the relation of the constants are now, because d is equals to 0, then what do I have? Well, it's just got this term equals to 0. So basically what we have here is a plus b is equal to c, right? D is gone, and then the second equation is this thing equals to c, so both are equals to c. So 1 plus 2ib a minus 1 minus 2i beta b is both equals to c, right? So if both are equals to c, therefore let's just write these are equals to this. So I got a plus b is equals to this thing. So 1 plus 2i beta a minus 1 minus 2i beta b. So let's try to simplify this. So if I bring beta, this is negative, so I bring it to this side, I got b plus 1 minus 2I beta b, and then this a here, I bring the a here, so I got 1 plus 2I beta a minus a, and then this is actually a cancellation, right? 1 times a minus a, so this term will disappear. This part is 1 times b plus b, so I got 2 minus 2I beta times b and 2I beta a, and in other words, the 2 will cancel, and I finally have what? I finally have b. B is equals to I beta divided by 1 minus I beta times a. Okay, so now I got a more, if I focus on the more special case, I got a simple expression for b in terms of a, right? And then also, well, a plus b is equals to c. I can also get c now, right? So since a plus b is equals to c, I can put this here, so a plus I beta a over 1 minus I beta. So if I make the denominators the same, both contains beta, 1 minus I beta plus I beta, so I cancel these two, right? So c is equals to 1 minus I beta a. Okay, so I got these two solutions now. Okay, and now I will define this quantity. I can define what is the tendency. So for a particle, it is something like probability, but it's not actually. Okay, but let me say use the probability language. So a particle incident on a delta function potential. From this solution, we have two possible outcomes, right? Two possible states. These are our superposition of states. Okay, it either gets transmitted or it either gets reflected. So what are the chances that the particle get reflected? What are the chances the particle gets transmitted, and vice versa? We define these chances by the coefficients, which we call reflection coefficient. Okay, so the reflection coefficient is defined by it's just called R. It's just the absolute value of b squared divided by the absolute value of a squared. And what was b? So it's just bringing down this. So if I want to find the absolute value, it's basically just equals to the absolute value of this thing square. Okay, and I think you guys are not fully used to complex number yet, so let me remind you, absolute value square is not just square, right? What it means is I take the complex conjugate and then times it again. So same up and down. So downstairs also I take the complex conjugate and then I times the bottom. Okay, so if not, then this is how a few of you were asking, you know, when you find the normalization of the eigenstate of the two-level system, you keep getting 0, right? It's not because it's square, it's complex conjugate times the previous one. And this will not make it, this will make sure that everyone here are positive numbers. See, minus I times I is just beta square, right? Beta square, and if you expand this bracket, you just get 1 plus beta square. Okay, and what was beta? Beta was, we written this down just now. Beta was m alpha over k h square. So this thing is just square of everything. So m alpha square over k square h4, and then this is 1 plus m square alpha square k square h power 4. Okay, so this describes the probability of an incident particle being reflected back. So this is okay, so just in words, R describes the probability. So I say in quotes because it's not like a probability that come from a normalizing your wave function, but it's kind of like proportional to a probability that an incident particle gets reflected back. Okay, so this is what we mean by reflection coefficients, and the opposite one is just the transmission coefficient. Okay, so I kind of like suddenly jump, right? Why b squared over a squared is because this is because of the reflection term. And then this was the incident term square, right? So transmission coefficient is similarly defined by the transmitted term and then the original term, or more incident term, to use the official words. And we call this T. What was the transmission term? So my incident term was AEIKX, right? And then the reflection was the other way, so B minus IKX. And then the transmitted is in the next region, continuing going to the right. It was CE positive IKX, right? So this is why we take C divided by A. So the C absolute value divided by the A absolute value. But C is, so it's just this thing divided by this thing. So you just end up with 1 plus beta square. In other words, this is 1 plus M alpha square K square H to the power 4. Okay, does that make sense? And we make an observation that why this is, I say the probability is because if I take T plus R, right, you get 1. So this is like the kind of like similar to probability. In what how much, let's say I have many particles in the same state, same K, being incident on the delta function potential. So what are the chances that a particle will get reflected back, and what are the other chances that the particle gets transmitted? So all the possible cases is just T plus R equals to 1. Okay, make sense? So this is how we got the reflection and transmission coefficients. I'm recording, right? Yes. Okay, so yeah, so I guess that's it for the delta function potential. And in this example, we introduced these two concepts related to the delta function. But actually, you can calculate reflection and transmission coefficient for any other potential as long as it is a scattering state, right? So let's make a few comments here. Should I? Yeah, let's write. Is there enough space? I think there is. Let's say scattering states for a general potential. So as long as it doesn't really matter what is the potential, as long as it's a scattering state. So if it's a scattering state, right, the scattering state, the leftmost region will have V equals to 0. Okay, so in my leftmost region, V is equals to 0, and then until something here, right? So until something here, then maybe V is not 0, so it's going to be something. Okay, but as long as scattering state, by definition, as long as it go to infinity, maybe it's not exactly 0, but it will approach 0, right? So this is the rightmost region. so V is approaching 0. Okay, and then the function is V0. Yeah, let's draw the potential energy, and then the scattering state could be anything, right? So it could be any shape, I don't know, yeah, something, whatever. But the main point is you can calculate the transmission and reflection coefficient in this situation as well, because as long as V is 0 here, or a constant, right, same story, or constant, then the wave function is still AEIKX, right? As long as E is higher, scattering state E is higher as you go away from the potential, then you got this thing here. So you got the incident wave, and then you got the reflection here, and then you got a bunch of solutions inside here. It depends on your problem that you are solving. It could be very, very complicated, and it could have multiple regions. Okay, but as long as until you reach the rightmost region, the solution is still some function. So let's call this CEIKX plus DEIKX, and this is for the transmit, and this is not relevant to our problem. So you can still calculate the reflection coefficient as reflection is B over A, right? It's the reflection term over the incident term, and the transmission is equals to the transmitted term over the original incident term. Okay, so yeah, in particular, right, this is where we have the quantum tunneling over here. So quantum tunneling, the calculation is very tedious, and I don't think I will waste the time solving it here, but you can find it on the paper, on the lecture notes. Right, so for quantum tunneling, right, it is because we have the potential energy is it is some constant, right, some constant as long as I am between 0 to L, and then it is 0 for otherwise. Okay, and then we take the scattering state, but my E is, well, scattering state is E is greater than 0, that will make me a scattering state, but it is less than V. Okay, so in this picture, my energy is like this. So my potential energy is 0 here, and then it becomes some height of V0, so that's a potential barrier, and then like this, right? So this is 0 and this is L, and then my energy is like this. Okay, so remember, right, when you're talking about Newtonian mechanics, the energy cannot access, particles with energy lower than V means it cannot access the region. So if you're incident from here, you cannot have enough potential energy to reach here, and therefore it is not possible to travel to this point if your energy is too low. That's why you need higher energy to travel from here to here. Okay, but for the solution, right, if you solve the Schrodinger equation, again, I'm not going to solve the details, but the method, we have seen it many times already, is the same. The method is this is x equals to 0, this is x, x equals to L here. Okay, so on this region, my wave function looks like AEIKX plus BE negative IKX, and then on this side, right, on this side is your energy is lower than your potential energy. So if you solve the Schrodinger equation, you are going to get CE, there's no I, so it's an exponential decay and exponential increase. So it's a constant x plus DE, another constant x. Okay, and then on this side is E is higher again, so it's a free particle solution. So free particle solution, you get a IKX again. So A, B, C, D, don't want to call this E because E is already the energy. So EF IKX plus FG E minus IKX. Okay, so in this solution, your K is 2me over h bar. And then if you go through the Schrodinger equation, which I'm not going to do it, but you will find that this is equals to, let's see, v minus e, right? 2m bracket square root and then h bar. Yeah, I think so. Okay, but if you go through it yourself and you can find out whether this is correct. But the k is the same here. Okay, and then you get the same thing. So this is the incident term. This is the reflection term. This is the transmitted term. And this part is not relevant. So in order to determine the relation, well, the relation between the constants should be the psi in region 1, right? For x is equal to 0 should be equal to the psi in region 2. Okay, and then the relation between the constant is the psi in region 2 must be equal to the wave function at region 3. So this is psi 1, psi 2, psi 3, right? And you in general you get 4 equations because you can let the derivative also to be continuous, to be this, and then the derivative sorry, this is not L, this is not 0, this is L. Okay, so this will give the 4 equation, and then will this give equations relating the constants, so A, B, C, D, and F, and then you fix G equals to 0, right? And then from here you can now calculate, if you can do this by calculating the reflection coefficient by taking the reflection term, which is modulus B square divided by the original term, and then the transmission is the transmitted term, which is now F divided by the incident term. Okay, so that is the quantum tunneling phenomena. Any question? So quantum tunneling is really a fully quantum effect that does not happen in classical mechanics, because how can this happen in classical mechanics? Cannot, right? If the energy is not high enough, you cannot climb across to reach the other side. But according to quantum mechanics, if you calculate this value, right, this is not going to be 0. Okay, so this is not going to be 0. So for the quantum tunneling, there is a probability that a particle that is starting from here, even though the energy is not high enough, it can somehow end up to be here. There is a non-zero probability. Okay, so this is how the scanning tunneling microscope works. Is because, right, for the STM microscope, right, what you have is the tip, which you need the kung fu to cut it out, right? So you need the tip, right, and then you join this to the ammeter, right, and then you join this to a current source, and then you got the sample. Okay, you connect this. Okay, then over here is my potential energy. So for my potential energy is is here, and then you got V0, and then you got here. So this part is the potential barrier. So originally, right, electrons can exist in this region. Electrons can exist in this region. Okay, assuming it's a conductor. So in the normal situation, the electron cannot jump from here to here, right, if the energy is not high enough. So how, in Newtonian mechanics, how do you have enough energy? You need to apply a strong electric field, right? Like when we did for the capacitor, with a strong electric field, the dielectric breakdown, the electric field is enough to push the electron with enough energy all the way to the other side. But for a normal situation, if you don't do anything, the energy is not low enough. But if you put the tip that is at the correct distance, then by quantum mechanics, you have the electron to have a non-zero probability to end up here. And once it end up here, it can jump into here. It means like you completed the circuit, and you can detect this as the ammeter. So if you measure the current as you move the tape over the sample, right? If you measure the current, the closer you are to the atom, the higher the current, the further away, the lower the current. By detecting the values of the current, you can actually plot the surface of the atom, surface of the sample atom by atom. And this is how you get this picture in the video over here. Where was it? Yeah, so you can see here is even it is a bit hard for even for this experiment. Like this is the hexagonal structure of the graphite, and I'm not experienced enough to operate this to interpret this diagram, but I'm guessing that this is like the atom part arranged in the hexagonal structure on the layer of graphite. Oh my god. Yeah, the case value will tunnel to another value, right? Maybe tunnel to 0 case or things like that. Okay, so that's the story about scattering and transmission for quantum states. So does anyone have any question about this? So this is interesting, right? It started, so quantum mechanics is interesting in the sense that it kind of covers everything from the most math and theoretical physics. You know, you derive the result, you do the calculation, you got this prediction, tunneling. And then people can actually do this experiment and build this device. You have seen the videos already. You have seen my friend doing the Kung Fu, right? So yeah, so you can actually do this, and then goes all the way until engineering. Nowadays, engineering students also are learning this. So it kind of speaks to how broad the applications of quantum mechanics have become until today. Okay, so I guess that's about it for all the examples of potential. Well, we have been solving a lot of examples of potentials, right? Before it gets too boring, we shift gears a little bit and we talk about incompatible observables. This is where the Heisenberg uncertainty principle comes in. Okay, so yeah. Why was there a notification? Okay, so later, right, we'll see that operators that do not commute with each other will have an uncertainty principle. Okay, so uncertainty principle, I think in your previous courses you have learned it in terms of X and P. We shall focus on that first, but there are, besides X and P, there are uncertainty principle for other observables as well, like angular momentum. But now let's focus on X and P first. Okay, so the uncertainty principle is going to be related to the commutator. So let's start by calculating the commutator between the position operator and momentum. Okay, so let's consider an arbitrary state. It doesn't matter what the state is, because I just introduced a state just because operator needs something to eat and spit out again, right? And I will use the position basis, so it can be expanded by this, right? So I hope everyone is familiar with this by now. Okay, it's kind of crucial. Oh yeah, Windows XP, Windows PX. So we're gonna derive a PX after this. So Commutator. Remember what's commutator? Commutator means if I take A bracket and B, right? Yeah, you guys know because you have already solved a few exercises related to this. Okay, it's basically A times B minus B times A. So when A and B, usually we think of them as matrices, right? And if you multiply a matrix, if you multiply it backwards, generally they are not the same, right? So if they are not the same, then the difference will not be 0. Okay, so only for certain special matrices you can make them 0. And not just matrices, even for the x and p operator. Okay, so let's do p times x first. So let's consider an operator p times operator x. So operator times operator, you're going to get a new operator, right? And let this act on some arbitrary state. Okay, so in other words, px is acting on this state in my position representation. Okay, px means x operate first and then p operate later. So let's operate the x. So operating the x into this state, it will just give me the eigenvalue, right, of this state. And then next I operate the p. So if I operate the p, what happens is, what does the p do on this function here? Remember that the p operator is the differentiation, right? So p is h bar over I derivative. So if I operate this inside, I will get h bar over I, and then I'm differentiating this with respect to x. So let us expand this out. H bar over I. So the constant, I can take it out. And then differentiating means 1 times psi plus x times d psi dx. Like this. Okay. And then let's open this bracket up. So I got h bar over I integral dx psi x, and then times this thing, and then plus h bar over I integral with respect to dx x d psi dx times this thing. Okay. Now this part is actually back to our original state itself. So this is just my state again. So what we have found is p times x acting on an arbitrary state is just h bar over I psi, and then plus h bar over I whatever this is. So let's just keep it like this. And let's call this equation 1. Okay? So everyone okay with these steps, right? This is nothing new because we have done things like this before. But now it's just to calculate this operator in particular. Oh, you guys are talking about Windows now. I think, according to many people also, I heard that Windows XP is still the best, less buggy, runs more smoothly and faster and easier to handle, especially when doing like research kind of things, when you need to do LaTeX, you need to do C programming. Okay, so now let us calculate the commutator. Well, to get a commutator, I need to see what happens for px, and also I need to see what happens for xp. There's the Windows XP coming in. So we're doing it in the reverse order. Okay, so reverse order means I want to know what is p first, and then you do x, right? So you operate this on the state psi. So which is to say that xp operating on my position representation, it looks like this. So let's put the p inside first. If I put a p inside, x will wait here for the moment. Okay, so you wait here first, and then p operating means is h bar over I, the derivative. Am I right? Like this. Okay. So now, now is your turn. Now you go inside. So the h bar over I is a constant. H bar go outside. The x goes in. And the x goes in. This one is just a number. So the operator doesn't care about scalar function. It just eats the state, the cat, and then you spit out the cat with the eigenvalue. What I'm trying to say is you get this. D dx like this. Okay, so now we see, well, we can see something interesting start to come in, because I want to find the commutator, right? So I'm going to do xp minus px. So xp minus px, I'm going to take equation 2 minus equation 1. So 2 minus 1 is xp operate psi minus px operate psi, is basically this minus this. Okay, so if this minus this, right, what happened? These two cancel each other out, so this two is 0. So should I write everything up? H bar over I, yeah, just write everything out so that it's absolutely clear. Minus H bar over I psi minus H bar over I integral dx, x d psi dx, x. Okay, so these two cancel each other out, and then again I'm going to use minus 1 over I is equals to I, so that my xp minus px is just positive I h bar psi. Okay, and then this part is, I can factorize this out. This is xp minus px. Both of them act on this, so I put the factorize the psi outside, and therefore what we see here is that the effect of xp minus px acting on a state is just ih bar times the state again. Okay, so, and also this is for arbitrary state. So since this is an arbitrary state, it is not an equation to solve for a specific state. It's for any state at all. This is arbitrary. If this is arbitrary, then the main point is these two operators are equal. Okay, it's an operator, so it's an identity operator with a constant, and this one is what we mean by the commutator. Okay, so this is IH bar. Okay, or sometimes you just write this IH bar, right? So sometimes we are too lazy to write the identity operator, because identity operator does nothing, so there's no point writing it, right? So that's why we got the famous equation. The commutator between x and p is IH bar. You might have seen this before in previous classes. Definitely an important equation in physics textbook. Anything that uses quantum mechanics, this is, you can say that this is the heart of quantum mechanics. So a lot of the strange quantum phenomena comes in is because of this commutator, right? So this is like the fundamental source of quantum phenomena. Okay, so we got the commutator, but I think we run out of time, right? So we will have to continue next week to prove the uncertainty principle. And just a bit of a preview or a teaser trailer, I don't know what to call it. The uncertainty principle, we will derive it, and the reason why we got the uncertainty principle is because the commutator is not 0. So actually, which is to say, right, uncertainty is not for every pair of operators. If the operator commutes, if this term 0, then there is no uncertainty principle. That means you can measure these two operators with 100% accuracy and precision. I forgot the difference between accuracy and precision now, but as long as you have two operators that do not commute, like this over here, then there is an uncertainty principle. You cannot measure both operators with precision. If you want to improve the if you reduce the uncertainty of one operator, the other one have to increase. So that is kind of why also where a lot of the strange quantum mechanics happen. XP is still a sort operator, yes, because yeah, in other words, we have the interpretation that XP, which is to say that XP minus PX is equals to a constant times the identity operator. So it is an operator, in particular is identity operator times IH bar. Okay. So let me ask you one thing. Is XP commutator a Hermitian operator? No, right? Because if you Hermitian, you get a negative, is no longer the same as before. So it is an operator, but it's not Hermitian. So it's not something that you can observe, right? So it's not something you can observe, but it is an operator in that sense, because it's a number times an identity operator. Okay. Yeah. So okay. Time is up. So probably let's not drag too long. We shall do the rest next. Was it Monday? Yeah, Monday. So let me stop the recording here.